Hello, welcome to another Midnight Maths video. In this one, we'll be exploring how to calculate Riemann sums to approximate definite integrals. I paused the video and read the question, and we're just going to get right into it. So, from the average value video, which if you haven't seen, I encourage you to watch it. It will be linked down in the description. We can quickly write the expression for t average. It'll simply be 1/8 times the definite integral from 0 to 8 of t of x dx. Now, if you don't quite know how we got here, that's okay, but just know that we're going to be calculating this quantity for all two of our sums, because we're going to be using a trapezoidal sum, like the question says, and we'll also use a right sum, so I can show you guys sort of the similarities between these sums, because really all these sums are almost the same. The only difference is sort of the shape of the sum, and that's all you really need to know. The formulae just kind of come naturally, and so in this video we'll sort of show you guys how that natural progression happens. So we start with a quick sketch. I always encourage you guys to sketch. So you've got a sketch of t of x. We know it's decreasing, so I don't quite know what the function is, but I drew a decreasing function, and we have 5 points, so I've put 5 points on here. So what does a trapezoidal sum look like? So it'll kind of look like this, where you make trapezoids out of every adjacent pair of points. Now this adjacent pair is going to be important, because like this adjacent pair is going to correspond to a spot on our table. It's going to correspond to that spot on our table. And so we're actually going to use adjacent cells on our table, because these points, because the points were, we've got adjacent points that make up the trapezoid. So one principle that applies to all Riemann sums, not just a trapezoidal one, is that you sum over, this is the sum sign, sum over the area in a single subinterval, right? And in this case, we're going to look at what happens when x ranges from a to b inclusive, where a and b are just some numbers, which then we can just like change the positions of a and b. So for example, if we know what this area is between that a and that b, then all we have to do is just shift the a and b over, and then find the new area, which would be this area. And then you shift it over again, and so on and so forth until you've shifted over and found all the areas. And we'll do the same thing with the table, as you'll see shortly. And that is going to be approximately equal to the total area. Now, of course, all of these are just approximations for the definite integral, so we have to keep that in mind. So let's get to actually computing this. So what I've drawn here is a small piece. What I've drawn here is a small piece, okay? So, for example, maybe what we did is we zoomed in on this portion, and that is what you get over here, okay? But it can't be any arbitrary portion. We're really just trying to figure out a general rule here, so you just keep that in mind. So our trapezoidal piece would look like this. And now what's the area of this piece? Well, it's the area of a trapezoid, right? So we know what the area of a trapezoid is. You can recall that's going to be 1/2 times the sum of the bases, which are b1 and b2, times the height, perpendicular height of the trapezoid. And note that, yes, indeed, we do have perpendicular height, so that's good. Now, we know that this and this are our two bases, right? Maybe one way that might be more familiar to you is to look at what happens when you rotate this trapezoid. So I've rotated it, sort of rotated it 90 degrees, and this is sort of what you get. So you can see here, right, those two sides correspond with these two. And so you know that that and that will be your two bases. So this what are the lengths of these bases? I encourage you to pause the video and try to figure it out yourself. The answer would be t of b for this base and t of a for that base, right? Because this is the graph of t of x, and since we're touching, since it goes all the way to that pink point that's on the graph of t of x, we can say that that's t of b and that's t of a, and that length would be b minus a, right? It's exactly the same principle we use for the definition of a definite integral. So we know that you're going to get 1/2 times the sum of the bases, which is ta plus tb, right? And then we're going to have an h, which is just b minus a. So this is the area of a single element, and we're going to just use this over and over again for all of the pieces and to figure out the total area. So let's select this, and then we will move it over here so that we can clearly see it. So now, how are we going to calculate this? Well, I told you earlier that we were going to use adjacent points. Well, these adjacent points are adjacent cells on our table, right? Because the neat thing is that the College Board has conveniently ordered the table from x equals 0, and they've ordered it in ascending order so that you can just use adjacent pairs of points to figure for your subintervals. But if they didn't do that, then you would probably have to order the table yourself. So that's just something to keep in mind. This is not some kind of blind algorithm you follow. So we were trying to calculate 1/8 times the definite integral. And so whenever you have these factors, I usually like to write them down first, just so that I don't forget to write them down later. And then, so we're going to have a sum of these pieces, right? So for example, this first piece, start at a, which is 0, and then it ends at b, which is 1. And then what we do is we keep moving. Then we sum over this piece, where a is 1 and b is 5. And then we go to this piece, and then we go to that piece, and so on and so forth. So we start with 1/2, and we could write 1/2 over and over again, right? Where we'd have this part repeat, like be different, 1/2 times something, and then add 1/2 times 1/2 times something else, and so on and so forth. But if you're calculating it, one idea might be to factor out the 1/2. So you would actually get 1/8 times 1/2, and then all you have to write down in the parentheses is just this blue part. So we end up having t of 0 plus t of 1, right? That's t of a plus t of b, and then b minus a is 1 minus 0, right? And then all we do is we just do this a bunch of times. So we keep on adding. So then what? Then we move to this subinterval where we get t of 5 plus t of 1, and then multiplied by 5 minus 1. And then we add the next piece, right? And that will be over here, right? So we would get t of 5 plus t of 6, and then 6 minus 5. And then the last one will be a t of 8 plus t of 6, and 8 minus 6. So that is sort of the expression you can calculate. Now, since they give you values of t, it's pretty easy to just plug in actual numbers here and then put this in a calculator or something. And once you end up doing that, you're going to get around 75.688. And what are the units for this integral? Well, it's an average temperature, so it's going to be in degrees Celsius. So this was the approximation for our average temperature that we got using a trapezoidal sum. The process is pretty straightforward, and you can also do this for any other type of sum. For example, we're going to do a right sum next, and the whole process will be pretty much the same. The only difference, like I said earlier, is the shape of the sum, which is the shape of each individual piece, and that's the most important thing. So let's do that for the right Riemann sum. So we have another graph right here, and we'll do the same thing. So right Riemann sum, we just use the right point of each subinterval to determine the height for that. So here in this subinterval where we are using these 2 points, we use the right point. And that's why it's called a right subinterval. So again, if we've got our little area, if we got a little piece here where maybe we zoomed in like that, right? Now we draw what this piece would look like again. So it would look like this. And that height is just a rectangle, so we can just do base times height. The height will be t of b, and the base, just like the trapezoid, is b minus a. So then the area of your single area element would just be t of b times b minus a. So then you just do this a whole bunch of times. Now we will once again calculate the average, which this is the exact expression for it, but we're going to approximate it. And in here will be our approximation for this integral. So we can start calculating this. So we start with this subinterval. And once again, this is a, and that's b. So we've got t of b, which is t of 1, times 1 minus a, which is 0. Note that we haven't written it on our expression that's in our table, right? So we continue. Now we're using this subinterval. So we've got t of 5, 5 minus 1, and then we're adding t of 6 times 6 minus 5, and finally we've got t of 8 times 8 minus 6. Now, once again, you can pretty easily put this in your calculator and figure out what the numerical value is. Before we do that, can you predict whether this value will be greater than or less than the value that we got earlier? I'll give you a hint. You can just use the sketch alone to tell you that. And this is a common theme that you'll see throughout a lot of AP-style problems. A lot of times, when you're comparing, you can just use sketches to get a comparison, a general comparison. And the answer will be that this approximation should be less than our other approximation, right? If we sort of superimpose the trapezoidal approximation on top of this one, you can clearly see that the trapezoidal approximation will definitely give us a bigger area for this case, right? And this might not be true in general. That's important to note. T of x happened to decrease here. What would happen if t of x was increasing? So if you compute this value, you get about 68.125 degrees Celsius as your t average. And that is indeed less than what we got earlier. So this was the process for the trapezoidal sum and the right sum. I encourage you guys to do a similar thing for the left sum and the midpoint sum. The process is pretty much exactly the same. Again, the only difference is you're looking at different shapes here, and that will dictate which formula you end up using to calculate the area of each individual piece. That'll be it for this video. I hope this was helpful, and I'll see you guys in the next one.